based on that empirical equation. So that's a very simplistic approach. I will give you a more detailed approach tomorrow. But now let's talk about what's a slender column versus a non-slender column. You know the difference between the two?
Again, depends upon the L.
A non-slender column fail in compression. A slender column buckles. That's the difference. Before we do anything with columns, few minor things one should know. These are at least 2 or 3 items. One of the items is that how do you separate the slender column from a non-slender column? That's one. If it is a slender column, what is the controlling factor, which is pi square A over L square, Euler's equation for slender column. The third thing you need to know is boundary conditions of the column. The L effective pi square EI over L square, that L is effective length. And typically people say that L over R below 24, 27 is non-slender column. In that range. Again, don't take that 24 as a gospel. It's not. And if you go beyond 27 or 28, then it becomes a slender column. Okay. What is R? Radius of gyration, which is square root of I over A. So those are the few minor things one needs to know. Again, I'm going to repeat myself, and I said this here somewhere, that very, very important for this, may agree, may not agree, ability of reinforcement to resist axial forces is neglected, unlike in steel, which results in lower GFRP column capacity. If you look at steel, for example, I'm just using that as an example. If you look at steel and try to establish the capacity, axial capacity of steel column, normally, as I told you before, on the lower side you have 2% of the area on the lower side of gross column area as the steel area. Okay. Normally we use about 3 to 4% of the gross area. As I told you this morning, never exceed 8%. That's a rule by the code due to many reasons. Keeping that aside, normally when you design a column, you're talking about 3 to 4% of the gross cross-sectional area. What I want to say here is important. The force is, they always have some reduction factors. I'll come to that a little bit later. But the message is, force, you're the one asking the question. Force is the stress times the area. Now, here we have 2 different kinds of stresses in steel. One is 4,000 or 5,000 psi concrete times the area plus 3%, 0.03, let's call it, times the steel area times the steel stress. So we already said the area is about 3%, means 0.03. But my message is the amount of stress that steel can take is about 8 to 10 times higher stress, I said. 5 to, say, steel is 40, 50 KSI, so it's about 10 times, So what am I trying to say? If concrete as a gross section takes 100 units, corresponding steel is taking 0.03 times 10, that's 30%. So you have a reasonably substantial amount of load carried by steel. So that is in terms of steel. This is where the conflict comes here. But here they are saying we are completely neglecting the amount of resistance offered by GFRP. On one hand, when you're doing all the computations, you're telling me that I'm going to go up to 60 KSI, but here I'm going to assume it's going to only take 5 KSI, or whatever that concrete F prime C is. Now they are going to argue that there is a micro buckling of FRP unlike in steel. Okay, which is fine, that is true. There is a micro buckling, we don't deny that. That's the reason we are not able to come up with an ASTM procedure to establish a However, the micro buckling is nowhere close when you are talking about the service loads. I mean, far from it. You understand the argument now?
Yes, sir. The micro buckling is
at the tail end of, exactly. Maybe it is beginning to buckle at 70 or 80%, but your service life is only at 20 or 25%. Now you got the point why I keep saying the buckling issue is an excuse. I mean, I shouldn't say it that way. Maybe I should say that they don't have the data to prove it. So I'm asking him, he's going to do the work to put a gauge or something and establish how much load the rebar is resisting.
Even in the column testing also, the cracks will appear almost at the 85% of the ultimate load.
Exactly.
Not at the 60 or 70.
That's right, because it's under compression. One of the good parts is it is under compression. Exactly.
Even the micro buckling will not occur because the concrete is intact with the fiber.
So why did they not include? I am guessing, I don't know, I wasn't there, because they don't have experimental data. If you have an experiment, this is where you all can fill in the blanks that are left open by us. So we don't have the data. You all have the money, can generate the data, and you have the brains to do that and challenge it. Unless you stand up and challenge means don't take my word wrongly. I'm not there to fight. It's a convincing argument where we believe it is right, So I believe it is going to be, for example, 60 KSI for GFRP, just like steel. They should be able to take that into account. All right. Now, that said, there are two reduction factors for a column capacity I'm going to talk. One is obviously a reduction factor corresponding to any of these materials, which is about 0.8 or 0.85. But the most important reduction factor is due to non-collinearity of the column top and the bottom. I'm not saying it is there, even though you call this a concentric column, we are talking about the slight bending, and they use 0.8 factor for reduction. If it is a tied column, they use 0.85 factor of reduction due to that non-collinearity if it were a spiral column. Okay. Some of that I will show you. Oh, it's right there. I mean, I said I'll show you. It's right there. So that factor 0.8 comes from that. So you can see, again, one can debate whether this factor is 0.8 or 0.85, but it's in that range. It's not 0.6, it's not 0.95, you know. And it's very difficult to get a perfectly collinear forces acting from top to bottom in any construction. That is that reduction is all about. And especially if you were, there is that, if you remember, I use the word 10% thing, you recall? If the applied load is less than or equal to 10% of this equation, that means you don't have to worry about any bending related issues. Okay, so if somebody can test it and prove that the bar is taking adequate amount of loading, I think it's well worth it, you know.
But even the rebar, if we consider the compressive strength will be almost, we are getting 60% of the tensile strength.
Correct.
So
Correct.
we may include the bar, resistance.
Look at it this way. The bar, let's say we're dealing with 100 KSI, then we reduced it to 90 or 80 KSI. Now you say it is, reduce it to, instead of from 100 to 85 or 80 to 60%, still it is equal to that of steel. That's my argument. So there some improvement can be made. Okay. With ties, it is a 0.8. With spirals, it is 0.85.
Sir, in the previous slide, where did we consider both the reduction factors? Where are the separate reduction factors? Like for the material and another
0.8 and 0.85.
Right there. 0.8 and 0.85.
0.8, the former 0.8 is for
Is a general reduction factor because of our basic uncertainty. That's a very standard reduction factor for columns in
eccentric case.
Accidental scientific.
yeah, accidental is the right
We
word.
can say initial imperfection.
Imperfection. Yeah.
Our one is accidental eccentricity.
Yeah. You can. Yeah.
Sir, if we get this reduction factor is different for spiral reinforced.
Yes. The values are a little bit different. Meaning, as I told you, 0.8 and 0.85. That's also coming from the steel code, except that variation is attributed to the confinement effect. So if you remember, have you done a concrete design course? If you remember, this the tie spacing should be less than 3/4 of the minimum dimension. You remember all that? Where is that coming from? Because when the crack forms, God forbid it won't, but even if it does, that crack is going to cut through the two contiguous ties, whereas you don't have that problem with a spiral. When if there were a crack. Okay.
Sir, but the crack will also across two consecutive pitch.
Huh?
But in the case of spiral, also the crack will have to cross two consecutive circles.
Yes. But the confinement effect is much more effective than in ties because of the continuity aspect of the spiral.
Who stress is continuous.
Right.
Spiral.
Correct. Okay. So I already told you that 10% thing, if your PU is not exceeding that 10%, then you don't have to worry about if it is the design comes into play only when PU exceeds 10% of your concrete stress times the area, which is the force. Nominal axial tension is standard equation, and AF min, whether you have any force or not or whatever, so you are talking about a minimum of 1% for columns. You must provide. Again, very similar concept to bending. You remember with the AS minimum we talked about? I told you how the FR rupture modulus based on that first crack, so you don't have a catastrophic failure. They call it here passive yielding. That's what they call it. FRP in tension must be limited to, again the same deal, 0.01. So these are the assumptions. Again, you can challenge that 0.01. This is again for very high bar diameters, where if I assume this to be a modulus of 6 million psi, this 0.01 to 6 million gives me 60 ksi. But if for columns we go up to 10, I think we limited it to 10. There was a debate of going to 12 number size. Number 10 means 1¼ inch. As the size increases, they're worried about FFU maybe going below 60,000 psi or 60 ksi. So if that were to be the case, so some of the codes, I think even we give the load, then you divide by the area, as opposed to giving you just one stress value like steel does. So we don't do that due to the shear lag issue. So the closed loop tie spacing is given to you there, not greater than 12 times the longitudinal bar diameter, 24 times the tie diameter, or smallest dimension, whichever is smaller, and obviously it has to be larger than 4/3. That's a pretty standard common sense. Minimum tie diameter, if you remember I told you, number 3, we don't have number 2, but we don't exceed number 6. Typically, that's where we are. Minimum overlap is 20 times D sub B, or 6 inches. Satisfy the stress up to 0.005. This is again an empirical issue. So the F, or the stress, and E, you were telling me the value is about 60%, for example. We have taken approximately 55%. Okay, but likewise, our compression modulus this is fair, extremely fair, 80%, which is, that's I don't know, is that what you're observing too? But what they did not observe, that is the problem. What they did not observe here is, that is true for an individual bar, but not a bar confined in concrete. See, we are talking about a realistic scenario. So that's why I keep encouraging you to put a strain gauge on the bar while you're testing a column.
Actually, we have tested this compression bar, only one single bar with different L by D ratio. So with L by D ratio 10, we observe that the E value is coming very less. That because of certain other thing, because since it is higher, so we are calculating for load deformation, right? So that buckling issues will come. But in concrete, it will not happen. So in concrete, it is.
That's my point. That's exactly my point.
Actually, the specimens should test under the triaxial pressure
Right.
to get the
Real, correct. But again, if you're going to test a concrete with FRP bar and put a gauge on the FRP bar, then you get a very realistic value. And what I'm saying is, those numbers will be much higher than that. So I don't know how you place a gauge. What we did, we leave a little styrofoam plug, and then we have a gauge, and then we bond it. We have a styrofoam plug, and then after concrete is poured, we dig it out and attach it to the wire. Now we have a wireless gauges too.
No, so we use we first with sandpaper we used to clean that place, and we have one Fevikwik kind of glue. So we just put it and paste it on that portion, so that wire will come out.
Yeah, well, you can do that. But now we are getting a wireless gauges. You can put it there and send a signal. You will get an answer. That's much easier. When I was a student, I put all these gauges we didn't have the wireless gauge at that time. So we used to put about 20 gauges a sample, to understand the whole crack profile, not just one location here.
Profile also you can get.
Right. Top to bottom. You see, this is particularly important in your case because you have end effects where you are applying the load, you have a much higher load concentrations than the ones in the middle or mid 70%. Top 15, bottom 10-15% is far more severe, than the mid 7. So you can get a good profile of that. Anyway, that is the discussion.
So, can you explain this in last comment?
Which one? You mean this one?
Yes, sir. FF count. What is the capital F?
Wait. FFD is the... No, all we are saying is FFD is the ultimate tensile strength of the GFRP. That's all we are saying. So that is, we already defined that in the sense that when you do the tension, then you have some reduction factors. After the reduction factors is what that FFD is. Okay?
What is the capital F in the starting? Capital F. No, sir. In the
So that in the equation, FF compressive. You're asking for
yes.
This one?
No. They're starting FF compressive.
that is
That should be small e. Minimum of second class like.
Young's modulus of incompression.
This is the Young's modulus of the under compression.
He's asking for that.
Yeah, that's compression. See the tension, okay, I thought you already understood. The tension values are different from compression values. It's not like steel.
Sir,
And remember another very important, when people keep measuring these, I hope he does, even for steel you have some ASTM procedures of how much is this aspect ratio, meaning the length versus the diameter. There it is a little bit more consistent than in FRP, because you will never ever get a consistent result in FRP in relation to length of the specimen versus D, because it is going to crush very easily due to Poisson's effect. That is why you doing the experiment in a confined environment, like he is talking about some triaxial machine or in a concrete environment, if you do that, you get a more accurate result. So this
first
is
term, sir, it is ultimate compressive strength of GFRP.
right.
The first
But you mean this one?
The first term, sir, in the line. FF compressive.
Right.
Ultimate compressive strength of.
Okay. You may get an ultimate compressive. For design purposes, you have to make all the correction factors to define that. That's what we are saying here.
Design compressive strength.
Right, design values. These are not actual values. So again, I don't think people fully understand, appreciate. Let me repeat myself. If I test 10 bars, let's start with the tension, then we go to compression. If I test 10 bars, I get values, whether it is steel or it is composite, doesn't matter. I get values falling all over the map. Meaning, suppose say I'm supposed to get a yield value of 60. Let's say that. When I test 10 bars, I get 58 for one, 64 for another, 59.2 for third, like that. When I average it, I'll get 61 or whatever. So we declare this value is 60. Okay, that is the average value.
Average of the ultimate.
Average of all the 10 tests. But that is not what they report as a minimum guaranteed value. So that minimum guaranteed value is the average minus 3 sigma. 3 times sigma. Assuming it is 8%, some number like that, or 6%, 6.5. So that multiplied by 1 minus 3 times 6.6, that's 0.8. Therefore, what they report guarantee for you is 0.8 times that average. So you see, that's the second one. And the third one, when you're ready to design, you're going to multiply with the CE factor and other reduction factors. So that's how you need to. So you don't even know what the average value is. What you know is average minus 3 sigma value. So I think there's a big confusion about all. It's even more difficult if you are going to look at it from the 95th percentile point of view. Yeah. So that gets it even a little bit more, perhaps more accurate, they say. Again, I didn't do enough work to say that. I'm only parakeeting what I hear people saying. So that is why you need to have a good clarity of what you're doing. Is that clear now?
Yes.
So that is what we are discussing here. I think that's where the confusion is. Column stiffness modifications for linear analysis. What is that? Okay, what is a linear analysis? What is a non-linear analysis? A linear analysis is that we are not accounting for P delta type effects. If you account for a P delta effect, that becomes a non-linear analysis. Give you an example. I'm sure a lot of you have heard Sears Tower, right? Sears Tower in Chicago. At one time, not now, was the tallest tower of the world, and the horizontal drift of Sears Tower under heavy wind conditions is approximately 14 inches. Not a whole lot, really, 14 inches from bottom to the top. It becomes one heck of a lot of a number when you multiply the P times delta, right? Delta is only 14 inches, but the P is zillion tons. That makes it drift more. That can be higher, the drift, due to P delta than just due to the wind as a first order analysis. So that gives you a perspective. Okay, now what they are showing you here, please look. For linear analysis, for steel bar, I-beam, 0.35 Ig, slab is 0.25, where Ig is the gross moment of inertia. Now they give you a more accurate formula for, this is all for steel, not for GFRP, right?
Yes, sir.
Now please look, the GFRP value, look at this, 0.7 versus 0.5. So obviously there is a penalty function here when it comes to GFRP compared to that of steel. So the moment of inertia of GFRP RC beam, again, look at how much of a reduction we are talking about. If you remember, for bending cases, we used what? You remember what we used for bending? 0.22. It is slightly higher, 0.25 here, because there is a column compression load. Unlike in your bending, we have like some kind of a pseudo pre-stress effect due to column compression. That's why it's a little bit higher. So this is, again, the egg or the chicken type issue we talked yesterday. These are the numbers we are going to start with for your linear analysis due to column frame drift. So you can see I column with the GFRP. These are all, again, empirical values. There is some theoretical basis for arriving at it, but by and large, they reduced it to some kind of an empirical value. So all these are given. Average, as I said, if you remember, the average rho of the steel percent is about 2.5%. In GFRP, it is of the order of 3 to 4%. This is an average. Yeah, typically we don't exceed 2.5 in steel. Once you exceed beyond 4%, you are going to get into the crowding of the bars in the formwork and inability to avoid honeycomb effects. And it's very important in columns, make sure that you don't have a honeycomb effect. It's important everywhere, but it's more important there. But anyway, my message is for this, these are the kinds of I values or the stiffness factor values we are going to be using for the first order analysis. Okay. KL over R. So I need to differentiate the swayed column from the unswayed column. So neglect the centerness effect in swayed columns when KL over R is less than 22. So for unbraced column, again sway, KL over R is 17. And we briefly talked about it yesterday. Somebody was asking me a question about it. And these are this is the ACI equation is this, that is kind of modified in this fashion for GFRP. This is the steel. You can see the reduction. Obviously, that is coming from lower modulus of GFRP. So, using that as a backdrop, now let's do the example. GFRP column. There are two things I'm going to do. I'm going to talk about column capacity example. Then I will be talking about axial bending interaction example. The two examples I will be dealing with. Here, a very simple column, 12 inch by 20 inch with cover of 2.5. We are assuming AS and AS prime area of FRP in the tension side and compression side are equal. AS is for the tension side, AS prime for the compression side. They're equal. For number 9 GFRP bar, number 9 bar is 1 square inch. I kept these numbers same. Therefore, the rho F is 0.038, obviously much higher than the rho F balance. It's a compression control. So if I do that, you can see the balanced value. This equation doesn't change as we talked about it this morning. That's what that equation is. And the balance value is 0.01 compared to 0.038. So they want that factor 1.4 is given to make absolutely sure you are not in any gray zone. 100% certain you are in failure under compression. That's that factor.
Always over reinforcement design.
Correct, always. Okay, now the section is compression control. Again, I repeat myself, GFRP in compression has same properties as that surrounding. That is where we are debating. That's where we need, somebody needs to stand up and challenge it. So here, from the force equilibrium, here are your two factors, sir. You can see 0.8 or 0.85. I'll leave it to you. So that the compression side must be equal to the tension side, and this is the strain compatibility equation. From here, we solve for that square. There's a 2 missing, I guess, here. FFT square missing. So my message is that number is less than 60,000. When will it be less than 60? Only when it is in a compression failure. Otherwise, it will be more than 60,000. And you call it a compression failure, get more than 60, there's something wrong. So then you solve for FFT. So the capacity of that for bending is 2702. The nominal axial value is given to you there, 0.854 F prime C. This is the area under compression only. That's one. This is the width, that is the effective compression zone, KT times D, right? That one? If you remember, if you go back. Yeah. You multiply that with the beta 1 factor. You remember that? That's how you get that. Where is that? That 4.32. There we go. 5.08 times 0.85. Okay. So the eccentricity, the max eccentricity is 15 inches for that column. Okay. Next. Tension control. I reduce the area of FRP to 2 square inches. And you can see that, and then rho F over rho FB. The computations are identical as before, except the areas are reduced to half, and that's why you see it's a tension control. That's the equations, that's the one we did this morning. That's an unrealistic number, the E value, right? So that is tension control. Okay. So this is how you establish the capacity of a column, both in terms of compression control and tension control. If you look at the tension control, you see you got, say, 1896 or 1900 inch kips. In a compression control, you got 2700. Stop and think about it. I kept everything same except doubled the area of GFRP. How much increase in cost do you think I had in terms of the overall column type thing? But I got a 50% increase in the capacity. So for pittance, for about few dollars of extra reinforcement, I got 50% increase. So as a designer, you need to optimize the response in this manner. So treat GFRP as having the same strength and modulus. This is for the column analysis and design to establish PM curve. What is that? Load moment interaction curve. I don't know, some of you may not know what is a load moment interaction curve. That's how it looks. What did you observe from that? Most important thing that one must be able to observe with a trained eye is that that point is constant, which is not true. That is from the assumption. See? No matter how much, how high, how great FRP you may have, but the code assumption is telling you that. That is the fallacy. Now, if I keep increasing, if I keep having some amount of moment inducement, then the load is going to decrease. For steel, you have PM diagrams somewhat parallel to each other. Not exactly, but something close to it. So that's the difference. I'll go back. Okay, now we are talking about design, right? So there again, we are talking about load factors, load combination factors, and all that good stuff. And that's what you are going to see here. Case 2, case 3, and all that stuff. Here is the load, dead load factor life. This is for a particular load combination. Load case 2 or load case, this is a combination. That's what we mean. For load case 3, this is the earthquake combination, for example.
Yes.
And this is a no earthquake type thing, and that is dead load, factor that, live load, factor that, wind load, and snow load. If you remember, I said most of the load factors are above 1. But here, when you get into the combination, it is that 1.5. Why? Because in combination with wind, snow is not going to be 100%. In combination with wind. That is the key word. You have, as I gave you, there are 8 or 10 load combinations here to check. Okay. And there's a load combination 3. So this is a PU. This is given. Inch capes, 15 and 20. MU1 is 600 and 700 inch capes. So step 1, find the column size. I gave you the bending moment or axial load requirements. So based on that, we are trying to find what is the size. That's right. That's the design. We are away from analysis now into design. So Pn max, if I have 0 moment, that is called Pn max. Means, what is a 0 moment? Sorry, I'm sorry, I'm going in the wrong direction. That is the 0 moment. That is Pn max, which is a very simple thing to compute here due to we don't even have to worry about the area of GFRP in compression, so it's just a one-step deal to establish that point. Then it gets complicated to sweep through this curve. So that is one step I said. You remember that? Pn max is 0.85. Pn max is 0.8. P0. And 0.85 F prime C. So from that equation, including the load reduction factor, that equation results in, for that load capacity of 600 kPa, a 271 inch square. A 17 inch by 17 inch column has 289 inch square. Check for slenderness effect. This is a thumb rule. What we are assuming, if the column has a bending column with critical buckling load, is roughly 5 times, that's a thumb rule. So this is the effective value between the column center to center is 18 minus 2 feet is the beam depth. So that is what you get. The K effective, we will talk about that later. I'm just assuming for illustration purpose, K effective is 1.5. So this is the effective value defined by the code. P critical pi square EI over K L square or L effective square. So pi square 4, 106. This is 10 to the power 6. K effective is, we're saying 1.5 or 1.9. And this is the 5 times, you remember I told you that's an empirical relationship, pi square EI over L square. And so the I value is about 26,000. So for a cracked section, we are going to assume 5 times the given load. That is where that 5 comes in. This is the given load after adding all your load factors. Okay. So that is the K factor. So the K factor, there is a way to determine the K factor. You have that bar chart. I don't know how many of you remember. Do you remember that? I don't think you do. I'm not sure I have all that. There is a special procedure of how you find a K factor in any kind of a complex multi-story building. What is it? Huh?
For braced and unbraced.
Unbraced, right. But I don't know how many of the people here know. I'm not sure. But let me leave it. No, I know. I don't know. Some of them may know, some may not. So anyway, all I want to say is there is a special approach of finding the K factor for a frame that is one set of what is it? Bar chart, like you call it. The K's are here and here, lower and upper for unbraced, and then one for braced. Okay, so we have that very standard. I thought I put it, but I'm not sure. At any rate, so the gross value required is 5 times pi square EI over L square type thing. That is the message. You found it? Yeah, that's fine. So, based on that, that is the moment of inertia requirement. From that, we have, if it's a square column, it is 4th 112 BD cube, B is equal to D, D4. That's where that 12 comes into picture. That is the 4th root of that multiplied by 12. Okay, so this is an approximate starting point to start designing a column for the given load, in this case, of 600 kips. You found it? You found it? Okay. Yeah. Wonderful. You can go ahead and explain. We use a slightly different approach, so you can see the effective K values, as you can see there. So you want to explain that?
We have beta 1 and beta 2 factors. So based on the conditions fixed and hinged. So this is.
I think the only difference is on that Q value if it is less equal than 0.04 in the top. If you go little up. First, when I say it top. That Q formula is given and the Q less equal than 0.04. That is, I think, in SI it is 0.05. I think.
We have a slightly different kind of chart than this, but that's neither here nor there. You follow your own approach in terms of establishing the effectiveness of the beams connecting at the top, including the slab, and the effectiveness, that K factor effectiveness of beam at the bottom. So that's all you have to do. So that's a very standard approach. Okay. So we arrived at a column size as a starting point. Step 2, find slenderness aspect of it by neglecting the slenderness effect, then conducting the first order analysis. The first order analysis is without the P delta, and also is based on empirical values that we gave you. What are the 5 times that? Then we have reduced I values. You remember?
Yes.
So that is the key word. So you will see that. Please see that here. So KL over R, that is the end constraint. They're all defined for you in chapter 6. The first order analysis, this is what I'm talking about. The reduction in the gross moment of inertia for the column is 0.4 due to bending effect resulting in cracking. At the service level, this is about that. This is, please note, this is a guide. For a T-section, 2 times moment of inertia of the rectangle with a flange. That's a guide. So the gross value of the beam, 112 BD cube, right? So keep it so simple. And then you find the reduction. This is again as per ACI. The cracked section for the beam, 0.15 times that. For the column, that. So this is what I'm talking about. Without going into the chart, this is one way you can establish the stiffness effect. That's what there are many ways to skin this cat. So this is one way to skin it. The column above, column below, beam left, beam right, that is your exactly. So the phi B, find joint relative stiffness below column. Again, based on the previous approach, 2.4, the alignment chart, there are, so once you establish sigma A for the top, 4.06, sigma B for the bottom of the column, 2.49, there is an alignment chart similar to what you showed. We have a slightly different alignment chart. That chart give me 1.9. That is your effective length. Obviously, since the top and bottom are partially fixed, you must get a value lower than 2, higher than 1. That's what you just showed. So, the slenderness effect, I over A. So, what does this mean? This means you cannot neglect the slenderness effect. Check the frame for sway or non-sway. Maybe we should stop. Oh no, we have some time. So find if the column must be analyzed as a sway or a non-sway. Again, there's a guidance given in the code. The load combination is provided there as per the code. So P sub U, sum of all factored column and wall gravity load at floor are considered for combination 3. That's found to be 200 kVs, while sum of the factor loads is 18,000. These are given to you. If they are not, you need to find out from the analysis. This is only, I made that very clear, all the numbers are only for illustration purpose. This is a fictitious number. So the story deflection, what is a story deflection? That's the drift. It is primarily dependent upon the horizontal loading. So it is something very close to, you can see, V is the force, L cube over 12 sum of the EIs. That is the equation given by the code for the first order analysis. Because of cracking of the joint, full fixity is impossible, hence factor 3 as opposed to 12 is used in the denominator as estimated deflection. If there is no crack, it will be VL cube over 3 EI. PL cube over 3 EI. Remember the cantilever thing? Good. Because of the cracking of the cross section, it is PL cube over 12 EI. But EI is a combination of all the columns that are resisting the lateral force along the whole story. So EI is given. So the delta is 0.33 based on that equation. Again, that assumption is from ACI. This is what they call stability index. This is the PU times the delta. You see that P delta effect now? But this is empirical, mind you, not second order analysis. That is the difference. So in a convoluted manner, we arrived at the delta effect in a very, very convoluted manner. And that's, again, this is ACI suggested procedure. Please look at section number 6643B. As per the ACI, for non-sway criteria, initially evaluate as per, which considers the end moments from P delta and evaluate it as a non-sway frame. Step 4. Now, what is that? We are accounting for P delta effect here in a indirect manner. That's what we are doing. I wrote here M1 is the first order moment from the gravity. M1s is essentially due to the lateral loads. So that's what we did. So all this anxiety is to establish these two moments. One is coming from the gravity, the other is from the lateral load effects. That's what we did. So one option is to come up with this A, and B is what we have shown you there. So the delta S, so not very close to option A of 1.16. A more accurate analysis will give you a closer result. From option A, we said that's not very close, but one can go with it if you want. The second order effects. Oops. So as you can see, the moment capacities are close to 1.4. End moments from the second order effect exceeded by 5%, which implies neither criteria is met, hence analyzing as sway column is met. So with all this, first we are establishing that the column is a swayed column or an unswayed column. So we establish that as swayed column with all that effort. That's the procedure. So if you look at the example of PM, I'll go over this tomorrow, but let me go over this in a broad brush manner today. So this is the given compression side area is neglected from GFRP for the PM diagram construction, and the tensile strengths are all given. The strain compatibility is given. I'll go over it again tomorrow. So I'm going to find the capacity of P for different C values. The compression block values of 4 inches, 13 inches, 22 inches, things like that. That's what I'm trying to do. Correspondingly, I mean, I'll go through this tomorrow again, but the message is that what is the capacity of the column with reference to bending moment when I have a C factor of 4, that is the C factor there here. If this C is 4 inches, if this is 16 inches or whatever, 22 inches, what is the corresponding bending moment? That's what I'm trying to find out. So, and I did that. There's a procedure, I'll explain that tomorrow, and you can see, I'll explain it carefully tomorrow. With the 0C, you have
Loading.
1958. For Mn for 4 inches of C, my moment is 4858. With 0C is 0 moment. For 13C, 7486, 2257. So, I'll explain that tomorrow. When I plot it, that's what I get, which is very similar to the idealized PM diagram that I showed as a very first or second slide of this example.
Sir, how did we decide the critical points? 0, 4, 13, 20.
No, I just picked some randomly, some points, like you could pick 3, 12, 20, not 4, whatever. I just, to construct in this random pick, what I might miss out is the peak value here. It's easy for me to find this value where P is 0, easy to find this value where M is 0, and the intermediate values, if I'm not careful, I may miss that peak. And then you have to multiply this with appropriate phi factor, exactly. And that reduction factor varies depending on the fact whether this section failed in compression or tension, whereas when it came here, did it fail in compression. So that is this is not the true actual design number. The design number is PU, not PN. So PU is with a phi factor, which that is going to be under this curve, within that curve, I should say.
So this PM diagram is not depending on this compressive strength of concrete or strength of bar.
Repeat it again. I didn't catch it.
Diagram.
Yeah, okay, I got
Is there
that.
any relationship to the strength of concrete and strength of steel?
Of course. Certainly, the Pn values or Mn values are dependent upon concrete strength. As the concrete strength increases, both will go up. That's number one.
So it's also considered for developing this diagram.
Oh, yeah. I mean, I will explain that tomorrow. Every step of the way, F prime C is a function. See? Every step. Whether it is C is 0, C is 4, 12, or 22, it's a function of F prime C.
Yes, sir. It was mentioned in the previous slides.
Right.
More previous.
Here. That is a function of F prime C. Pn is what? Remember? F prime C function. Very early on. I'll explain that to you tomorrow. Please look here. What is that? Concrete strength. F prime C. So it is a function of F prime C, but it's a highly convoluted approach, and you do need this for design of, whether it is a numbers may be different, but the procedure is same, whether it is a steel or FRP. It is a little bit more involved with FRP because of there is a couple of more complicated empirical equations, but the philosophy is same. The reason I keep saying that is, don't be scared about it. So most of you are aware of how to design these with steel, so it's a matter of tweaking it for FRP. So that I'll repeat this tomorrow. So any questions after this? We are exactly 3:30. They want to ask questions from now for the day.
maybe participants can try some of the examples from 1 to 4
Uh-huh.
by using SI units.
Yes. You can try that. And if you have questions, you can ask me. That's a good homework, he's saying. So,
Because
yeah.
in
An
India,
idea.
we are more SI units.
Familiar to-
Right,
We are
right.
very comfortable to understand the behavior also from the SI unit.
Sure. Yeah. Another thing is, I will leave my book. I don't have another copy of it, but later, that's after tomorrow. But this book also has examples. And I think, if I'm not wrong, there are some examples in SI units. This is a workbook. I'll leave it with the Professor Prakash, so you all can refer to it, or if you have any questions, communicate with them. But tomorrow I'll go over it. I just broad brushed it today just to give you how a PM diagram is constructed. That's a very basic fundamental thing. I'll repeat it tomorrow. Any questions? That is why I attempted to provide as many details as I could, both in terms of numbers and also in terms of explanation. And all this would make a much better sense if you read through these examples with the code next to you. Without the code next to you, you may be a bit confused.
There is a slight confusion, sir. There are many, the reduction factors are being applied at many steps. That's a
Yeah.
The design is to be kept as an engineer safer side. That's why we are doing the constraints.
According to the Indian codes, the reduction factor is usually implemented at 1 or 2 steps generally. They combined all the types of reduction factor in one number and just multiply it once. But here,
that leads to a higher penalty in terms of, so you get a more conservative design. But here, by having these factors, so you have a choice where you want to apply some factors in a given structure. If you may not need the same reduction in a different kind of a structure.
That is more concepts now.
Right.
You understand.
In India, column design, if I consider, so we start with 0.4 into AC into FC plus steel. But here 0.8 into 0.85.
Correct.
The
That's-
point 447 is also coming like it's because we first of all we use the tube strength. We convert it to
maybe
cylinder.
cylindrical.
Then we multiply the factor, which is 0.85. That is. From there it is coming to 0.85, and then it is then 1.5 we divide the material safety factor by 1.5, so it comes to 0.447. For column again we reduce for the accidental eccentricity.
That's a lot of penalty.
Yes.
Yeah. But in spite of it all, why your structures are not as durable, I don't follow. Is there some material issue?
Yes, actually one thing Professor Surya told in morning, that is water cement ratio. It's very hardly controlled in normal.
Well, I thought you all said now we are controlling it with 0.4.
Yeah, but in lower level, or say like not that much supervised constants.
I'm quite surprised you were the Bombay, what is that, bridge or road, you have it in the sea? What do you call that thing? Yeah, there is some kind of a loop or a diversion. I do really wonder how long that would survive. You know what I mean? It's all right when it is new. Come 20 years, what happens?
Already it is 15 years old, I think.
Somebody told me one of the bridges failed in the, I mean, they don't tell you. Failed means whatever the excess deflection, they fixed it, but if it's only 15 years old, imagine.
So the margin in the contract is also issue in India. It's like if someone applies for a construction tender, then the rate margin is too much,
Too small,
too small for the contractor.
too little. But the question one has to ask is, you need to increase the margin, After all, these are supposed to be the iconic structures for, long-term productivity of the country, right?
At material level, the production is good. The provisions are quite nice.
But the execution is
The
bad.
execution. The problem is that the execution.
But this is the general procedure we apply.
So there is a request,
Huh?
actually, that we can keep some more emphasis on deflection and crack width, because we could not understand that properly. Yes. Deflection and crack width.
In GFRP.
One more example for that.
Eventually, we have to go through this exercise in parallel to steel, to convince people. But eventually that may happen. Meaning once you gain enough confidence, you run 20 design, every design is a failure in controlled in terms of deflection and crack width, then you forget about the load part of it and only focus on, it may come to that, Anybody from online?
Anybody? Can we allow bundled bars in non-construction using FR?
Again, they said no for now because there is no data on bundled bars. For now. No, I said concrete people are wonderful with a lot of design insights and what have you, which is true. But at the same time, they're very restrictive because they don't have a mathematical approach to hang their hat onto. They always fall back on experimental data.
So in RCC concretes, there is much flexibility in choosing the diameters. Like talking about the area of steel methodology, we can choose any diameter.
How big a bar you go to in steel?
What's your limit?
18, 22? I heard you have a bar number 22, like almost close to 2 inches. 20 or 20?
Maximum
32 mm is the largest.
32 mm.
Yes, that.
Okay, that is 10. That is 10. 36 is 12. But actually FRP has it now up to 10 or even 12 they have in the code.
40 mm, up to 40 mm.
That may be in steel, not in FRP.
FRP.
Oh, there is? Oh, maybe your code. Oh, okay. Yeah.
Is it better to provide smaller diameter bars of large media than the large diameter bars of smaller media?
from the bond point of view.
Obvious that smaller diameter bars of large numbers will give you, assuming you satisfy the spacing requirements or whatever, assuming that smaller ones of large numbers will give you a much better bond. Anyway you cut it, the shear lag would be low, the bond strength will be high with smaller diameter bars. That's the way to go. But will you be able to satisfy the spacing requirements? It's always one thing or the other. It's a balancing act.
So is there any limitation of the percentage of reinforcement in any?
Of course. I told you 8% for columns, 4 or 5% or 6% for beams. 4% I think.
Indian code it is 4%.
Yeah, same with us too. Yeah. You don't want to exceed that kind of. Unless we come up with a better definition of how the compression GFRP controls, otherwise we will never be able to make a doubly reinforced beam, and what max percentage you are talking about. All these cannot be well defined without
Analysis of
compression side. Exactly.
Can we provide two different types of NMR code, like GFRP bar and CFRP bar? CFRP will have more stiffness. You can
Hybrid reinforcement.
Well, the hybrid systems, like I said, have certain limitations for the time, unless we overcome. I heard Professor Prakash wants to do some hybrid stuff.
My column I was.
Yeah. Then he understood when I was talking, because of the incompatibilities that might lead to other issues, They're not accepting the all composite, forget about the hybrid bars,
If thermal conditions are kept constant, then if we have like
Sure, absolutely. If the thermal conditions are constant, for example, meaning there is no freeze-thaw type effect, or for that matter, if the freeze-thaw effects are not there, your crack growth or shrinking may be minimal, then you may not have as much of a problem even with steel. Look at it that way. Maybe different if you're wanting to use fresh water or seawater, keeping that component aside, but we are really pushing for seawater usage, sea sand usage. So then right off the bat, your sand mafia will be gone, right?
Any other tools?
Let us meet tomorrow instead of today. They want a couple of people coming from. Yeah.